طيب, hello Yasif. So today we said that we are going to make revision, يعني general revision على acid base equilibria chapter. وطبعا we are going to solve some problems or some questions. Starting from the beginning, we said that if we have, so here we have acid. So we said that if we have an acid at the beginning, the MCQ questions can come that if you have an acid like, for example, hydrochloric acid plus water, for example, then this will give us H3O positive plus chloride ion. So from the beginning, we know that an acid is a proton donor according to the Bronsted-Lowry concept, our Bronsted-Lowry definition, that an acid is a proton donor and a base is a proton acceptor. So here, hydrochloric acid donated its proton to the water. That's why we call hydrochloric acid, we call it acid 1. And when the hydrochloric acid gave its proton to the water, it formed the chloride. So we call this base 1, because sometimes in the MCQ questions, they tell you to write which one is acid 1, which is acid 2, and that's yani. So we have to know that acid 1 gives base 1, and then this we are going to call it base 2, and this is going to be called acid 2. So here we are going to say acid 1 will give base 1. Don't say acid 1 base 1, but it is acid 1 base 2 gives acid 2 and base 1. And we call these two acid-base conjugate pairs. These are called acid-base conjugate pairs, and these two are called acid-base conjugate pairs. And sometimes they will give you other reactions. You see which one gave the proton to the other. As we said before, that here if we have something like sulfuric acid reacting with nitric acid, although both are strong acids, then we will see that sulfuric acid is more strong than nitric acid, and that's why the sulfuric acid is the one to donate its proton to the nitric acid, forming HSO4 minus plus H2NO3 positive. So acid here, acid 1 is the sulfuric acid and its base is base 1. Nitric acid will be base 2 and H2NO3 will be acid 2. Now, how can we know whether we have a strong acid or a weaker acid? From the Ka values? We know that as the Ka values are high, yani the greater the Ka values, or the bigger the Ka values, the stronger is the acid. So sometimes they will give you two acids, maybe they are unknown to you, but yani you don't know whether it is a strong acid or a weak acid, whether it is which one of them is stronger than the other. Of course, we determine this from the Ka value. The bigger the Ka value, the stronger is the acid, and the smaller the pKa value, the stronger will be the acid. Now, how do we calculate the pH? We know that pH is equal to minus log. pH equal minus log the hydrogen ion concentration. The pH equal minus log the hydrogen ion concentration. If we have a strong acid, at once we say that the concentration of the acid is equal to the concentration of the hydrogen ions, because the dissociation is complete, or the ionization is complete. And so here, if we start with 0.1, for example, mole per decimeter cube, it will give us 0.1 mole per decimeter cube for the hydrogen ion and 0.1 mole per decimeter cube for the chloride ion. We don't bother ourselves by the chloride ion, so at once we say that the pH is equal to minus log 0.1, and we get the value for the pH. Now, what if we have a weak acid? If we have a weak acid, then we say that, for example, if we have something like CH3COOH, it partially ionizes, because this is the definition of a strong acid, that it completely ionizes in water, whereas the weak acid partially ionizes to give the H positive plus the ethanoate ion negative. Or in general, we can write HA gives H positive plus A minus. And so here we say that whenever we have equilibrium, there should be an equilibrium constant, and here we call it the acid dissociation constant. The acid dissociation constant Ka is equal to the H positive times the ethane weight ion negative divided by the concentration of the ethanoic acid. So here we cannot say that the hydrogen ion concentration is equal to the concentration of the ethanoic acid, because here there is partial dissociation, not complete dissociation as in the strong acid. So we cannot say that they are equal. And that's why here we are going to say that since in the dissociation, we got the Mohr ratio 1:1 with respect to the hydrogen ion and the ethane weight ion, then we can say that it is equal to H positive squared divided by the concentration of the acid, whether the acid is methanoic, ethanoic, pentanoic, whatever. And so from here, we say that the hydrogen ion concentration is equal to the square root of Ka times the concentration of the acid. And then we get the pH, which is minus log the value that we are going to get from the upper part. So here we considered the concentration of the ethane weight ion is equal to the concentration of the hydrogen ion, because they are produced in a Mohr ratio which is 1:1. Now, sometimes they will ask you, what are the assumptions that we made here? There are two assumptions that we did here. The first assumption is that we assumed, please, if you have any question while I'm explaining, raise your hand. I'm going to ask you what is your question. Whenever you have any question, please ask. So here we have two assumptions made when we have a weak acid. What are these two assumptions? Sometimes they ask about them in the exam. So for the first assumption, we say that the concentration of the acid initial is equal to the concentration of the acid at equilibrium. So the concentration of the acid initially is equal to the concentration of the acid at equilibrium. And this is, of course, not true, because we considered that the concentration here we substituted by the concentration of the acid that is given to us in the problem, although this is the concentration of the acid at the beginning, without being dissociated. Although the dissociation, yes, is so small, but still part of the ethanoic acid dissociated into H positive and ethane weight ion. We, as an approximation, or as an assumption, we consider that the concentration of ethanoic acid initially is equal to the concentration at equilibrium after it dissociated. This is the first assumption. What is the second assumption? The second assumption is that the hydrogen ion concentration due to the dissociation of water, is neglected. We neglect the hydrogen ion that comes from the dissociation of water, because ethanoic acid dissolves in water, which means that water is present in this equilibrium, equilibrium and equation. The water is present, yet we neglected the hydrogen ion concentration that comes from water. We neglect it. We do not consider it at all. And there is a third assumption that we did here, is that the concentration of the H positive is equal to the concentration of the ethane weight ion. Sometimes they write it in the mark scheme, but I prefer that you mention these two better than to say the hydrogen ion. It's not wrong. If you say the hydrogen, we assume that the hydrogen ion concentration is equal to the ethane weight. We did here in this part, we did it here. We assumed that both are equal, and that's why we placed H positive squared. You don't get the first one? Here we say that we considered the concentration of ethanoic acid initially is equal to the concentration of ethanoic acid after equilibrium. Is that true? Of course not, because if you, for example, start with 0.1 mole per decimeter cube of ethanoic acid, then it dissociates into H positive and ethane weight ion. Will the concentration of ethane weight ion of ethanoic acid remain 0.1? Well, it must be changed. What do you think? What do you think, ya Hamza? Is the concentration of ethanoic acid before it dissociates the same as after it dissociates? I can't hear your voice. It's no, but we consider it. We consider it to be like that. We considered, we assumed that the concentration of ethanoic acid, that's why we substituted here in this equation by the initial concentration of ethanoic acid. If I start with 0.1, I substitute here by 0.1. So this is an assumption we did. Okay, but you understand now? You understand it now? Tamam, okay. So this is the second assumption that I prefer that you say, but this is not wrong if you assume that you write from the assumptions that we assume that the hydrogen ion concentration is equal to the ethanoate ion concentration, okay? So now we know how to calculate the pH of a strong acid, how to calculate the pH of a weak acid. Now, how can we calculate the pH of a base? If we have a strong base, and this is the only case that we are going to discuss, if you have a strong base, like for example, sodium hydroxide, it also completely dissociates into sodium ions and hydroxide ions, which means that if I started with, for example, 0.2 mole per decimeter cube of sodium hydroxide, it will give me 0.2 mole per decimeter cube of the hydroxide ion. So how do we get the pH of such a solution? We have seen that we have something called the Kw, which is called the ionic product of water, which is equal to 1 times 10 to the power minus 14 mole per mole square decimeter minus 6 in case of at the temperature of 25 degrees Celsius. And so we have known that also the Kw is equal to the concentration of the hydrogen ion times the concentration of the OH ions for water. And this means that the concentration of the hydrogen ion is going to be equal to Kw divided by the concentration of the hydroxide ion. And the Kw is 1 times 10 to the power minus 14. And you substitute by the concentration of the hydroxide ion, which is the same as the concentration of sodium hydroxide, 0.2. And you get the hydrogen ion concentration, from which you see that the pH is equal to minus log the value that you get here. So this is how to calculate. But sometimes, for example, if they say that we have barium hydroxide, so barium hydroxide, take care that when it ionizes, it will give us barium ions plus 2 hydroxide ions. So if you start with 0.1 mole per decimeter cube, it will give you 2 times 0.1 mole per decimeter cube of the hydroxide. So take care, because sometimes they bring other hydroxides other than sodium or potassium hydroxide. So we have to see how many moles of hydroxide ions are present in the base, and we substitute using the value. So from which we can get the hydrogen ion concentration by dividing the Kw by the concentration of hydroxide ions, and we get the pH value. Now the Kw shows us that it has a specific value at 25 degrees Celsius. This is at 25 degrees Celsius. Now what happens to the Kw value when the temperature increases? We know that the water by itself, pure water, is very, very, very small dissociated, because as a pure, the dissociation of water is very, very small into hydrogen ion and hydroxide ion. But this dissociation becomes bigger when the temperature increases. When the temperature increases more than the 25 degrees Celsius, the dissociation of water will be greater towards the right-hand side. It will be not completely towards it's not going to be a complete dissociation, but it will lie further to the right-hand side. It means that the concentration of hydrogen ion increases. At higher temperatures, we'll see that the Kw becomes higher, because the Kw is equal to the concentration of hydrogen ion times hydroxide ion. The Kw will be greater than 1 times 10 to the power minus 14. And when they ask you whether water will be still neutral or not, فيس يعني we see that the water is still neutral even if the Kw, even if the dissociation is greater. It means that there will be more hydrogen ion concentration. But since the more ratio between the hydrogen ion and the hydroxide ion is 1:1, so the water is still neutral. But we will see that the pH will be less than 7. It is less than 7 because at higher temperature, there will be more dissociation for the water. So the hydrogen ion concentration will be greater than that at 25 degrees Celsius. And since the hydrogen ion concentration became greater, we'll see that the pH will be less than 7. But still, the water is neutral because the more ratio between the hydrogen ion and the hydroxide ion will be the same. They are still the same, so water is still neutral, but the pH will be less than 7. Okay, so please take care for this. Now, we have taken that if we make dilution to a strong acid, like, for example, hydrochloric acid, if I started with, for example, 1 mole per decimeter cube of hydrochloric acid, if I diluted 10 times, if it is diluted 10 times, it becomes 0.1 mole per decimeter cube. And then if I dilute it to be 0.01, yani every time I'm diluting it 10 times. Yes. Yes, yeah, Ryan. So if we are diluting the concentrated acid 10 times, then we will see that the pH will always change by 1 unit. Yani you will see that if you calculate the pHs here, you will see that the difference between the pH will decrease by will increase by 1 unit. Yani always there will be a difference of pH equal 1 unit. And if you calculate, I don't know the values exactly, but if you calculate let me see it كده.
It will be 0, 1, 2, 3.
Here if it is 0 8.
0, then 1, then 2, then 3.
تمام, thank you so much. So here you will see that as we calculate the pH of a strong acid, as it is diluted 10 times, as you see here, it is diluted 10 times. So here diluted 10 times, you will see that the pH values will differ by 1 unit, from 0 to 1, from 1 to 2 to 2 to 3. But of course, it will reach a certain value where it will, if the concentration of the HCl is equal to 10 to the power minus 8 mole per decimeter cube, then do not say that the pH is 8, because it is an acid. It is a strong acid. How can the pH be 8? So we say that only the pH equals 7. This means that here water is the one. If it is very diluted, this means that the water is the predominant substance that is present in the solution. And so we say that the pH equals 7. If you are having, this came in exams, I'm not saying something that is very simple. Sometimes they bring it in exams. But if we have a weak acid like ethanoic acid, and they also diluted 10 times every time, you will see that instead of, here also the dilution is 10 times dilution, you will see that the pH, when it changed only 0.5. If you calculate the pH here, as we did above here, you will see that the difference in pH will be 0.5 only. The difference between the pH is 0.5. It's different than the acid because the acid completely dissociates, whereas the weak acid partially dissociates. Okay, so this is how to, this is, for example, here it is 2.38. This is 2.38. You will see that this will be 2.88. This will be 3.38, and so on. So you will see that the pH decreases by 0.5, increases by 0.5. طيب, let us go to the titration. Yes, Ahmed.
Miss, can you repeat the HCl pH 7?
If the hydrogen ion concentration is 10 to the power minus 8, and you take minus log 10 to the power minus 8, it will give you a pH of 8, right? So how can an acid has a pH of 8? We know that the acids are from pH 0 to pH before 7, isn't it? So how will it be pH 8? If you have a concentration of HCl that is 10 to the power minus 8, do not say that the pH equals 8. You have to say that the pH equals 7, because here the water is the main substance in this solution. It's not the acid. So the pH of water is the one that will form. خلاص? You understand it? Or still you have a question?
Yeah, thank you.
You're welcome. Now I want to show you the pH titration curves, because some of you, when we draw the titrations, they will ask me, and they usually ask me, where should we start and where should we end? Okay, so let us see here in your book. I'm sharing the book, so if you can't see it, please tell me. Can you see the book or not yet?
Yes, miss.
Yes, miss.
Okay, thank you so much. So when we make a titration between a strong acid and a strong base, so you will see that here, if here we started with the base, so we will start with the pH between 13 and 14. This is the pH of a strong base, and we are titrating it with a strong acid like hydrochloric acid. It means that at the end, the pH will be between 0 and 1. You will see that the curve here, as we said, there is no change, except there is a very, very small gradual decrease in pH because the solution is being diluted. And then at the equivalence point, there will be a drop, a vertical drop, until we reach the acid part. Now, as you see here, that the pH vertical line will be between, and if you are titrating, if they bring you to draw a titration curve between a strong acid and the strong base, so the straight vertical line should start from 3.5 to 11.5. It should, this vertical line, of course, here they did it a little bit, little bit up, like it should be from 3.5 to 11.5. And you will see that since we have a strong acid titrated with a strong base, the midpoint, كمان it should be less than that كمان, لأنه the midpoint should be in the middle between them. And here the midpoint is 7. If this is 11.5, so there is 1, 2, 3, 4.5. So here 1, 2, 3, 4.5. It's about كده. It's about كده. But you will see that the 7 is in the middle. دايما draw the pH at the equivalence point to be in the middle between the lower and the higher pH at which you draw the vertical line. The vertical line should be so that the pH at the equivalence point, here it is 7. Why is it 7? Because when we titrated sodium hydroxide against hydrochloric acid, we got the salt, sodium chloride, which is neutral. So since the salt is neutral, then the pH at the equivalence point is 7. So you have to draw the vertical line so that the 7 is in the middle. You start with 3 and you end with 11, for example. Okay? What if we started with the HCl? If we started with the HCl, so the pH is here. We start from here. So let me draw it in a different color. So we start from, if in the conical flask there was HCl, then there will be a gradual change until we reach the equivalence point, and then we go up, and then after the equivalence point, it will be like that. Okay, and you draw it in the opposite way. So what about if we have, if we are titrating here a weak acid with a strong base? So they started with a strong base. The weak acid, its pH should range between 3 to 5. Okay, from between 3 to 5. So if you titrate a weak acid like ethanoic acid, if you titrate the acid like ethanoic acid with a strong base like sodium hydroxide, then you get sodium ethanoate and water. Now, what about the salt that is formed at the equivalence point? It comes from a strong base and a weak acid. This means that the pH should be higher than 7. and usually it's about 8.5. Yani about 8.5. So this is the pH at the equivalence point, because the salt that is formed at the equivalence point is basic. It is basic because it comes from a strong base reacting with a weak acid. So the pH at the equivalence point will be about 8.5. So as you see here, that we start from about 5 or about 5.5, let it be even 6, for example. We start with 6 and we end up with 11. Yani the vertical, please write the numbers so that when you draw a titration curve, you adhere to these numbers. So we start here. We started the vertical line from 11 and we end at about 6 or about 5.5. And the pH should be in the middle. Yani this part should be equal to that part, nearly. It's not exactly, but nearly. It is nearly equal. Okay. When we are titrating at the opposite, we are titrating a strong acid with a weak base, and we started طبعا if here let me show you something. يعني here titration of a weak acid with a strong base. Now what happens if we are doing the opposite? If you've started with the weak acid, you will start with a pH between 3 and 5. So for example, it is here, for example. So here we have to show that there will be a hump like this. Yani there is a rise in pH for the weak acid. There will be a rise in pH and then a gradual change. And then there will be a gradual change until we reach the equivalence point. We go up and then you will draw the curve like this. So this is, yani, take care that here you make a jump like this, a little bit jump in the pH and then the gradual change and then the equivalence point. If you remember, we said that here, why is this jump happening? Because this part, we call it the buffer part. And we know that in the buffer part, in the buffer region, there is a gradual change in pH. There is no big jump in the pH. There is a gradual change because the buffer is resisting the change in pH. But here in this beginning, or in this first part, there was a jump because we didn't reach, yani when they ask you why there is a jump here, you say because we didn't reach the buffer part. And so any addition of the base will affect the pH of the solution, because we say that the concentration of the acid here, the concentration of the acid, which is a weak acid, is greater than the concentration of the hydroxide ion or the base that we are titrating it with. We are still having a high concentration of the acid. We didn't reach the buffer region yet. So any addition of the hydroxide ion, it will cause a rise in pH. The pH will be greatly affected because we didn't reach the buffer part yet. Okay, so always when they ask you why there is a jump here, you say that the concentration of the acid, of the weak acid, is much greater than the concentration of the hydroxide ion. We didn't reach the buffer region yet. And so any addition of the hydroxide ion will cause a rise in pH. Okay, so you have to draw it. If you start in the conical flask with the acid, you will start from between 3 and 4. You draw a jump and then a gradual change until you reach the equivalence point. And then you, because it's a strong base, you will reach about between 13 and 14. So what is, if the titration was between a strong acid, like for example, hydrochloric acid with a weak base like ammonia, then here we will get the ammonium chloride plus water. From where did the water come from? It's because ammonia is aqueous. It means ammonium hydroxide, but we usually write it aqueous ammonia type. So here we have ammonium chloride salt that comes from a strong acid and a weak base. So the strong acid will win. It means that ammonium chloride is an acidic salt. Acidic salt means that the pH is at 5.5. So you start here from about 8, the vertical line that you are going to draw. Start from about 8 till 3. So from 8 to 3, if you subtract it, it's 5. So this means that you go down 2.5 and up 2.5. So it will be, the pH will be at 5.5, whereas above here, when we had the strong base with weak acid, the pH was at about 8.5. Okay, please, you have to know these values because when you draw the curve, it's important to draw such things. خلاص, you understand? طبعا if we have a weak acid titrated with a weak base, we don't show any vertical lines. You see, نسيت أقول لكم هنا also, you see that the curve, we started with the weak base. There will be a drop here. There will be a drop in pH before we reach the buffer region. As we did in the acid, there was a jump. As I told you here, there is a jump before the gradual change. Here, there will be a drop before we reach the buffer region. Okay? If we have weak against weak, then we start with the pH of the weak base, for example. We draw the drop and then the gradual change. But here, there will be no vertical line because both are weak. We draw just an inflection point like this and then go to the other side. And the equivalence point, because here, if we are drawing ethanoic acid with ammonia as they did here, then the salt will be neutral. The pH will be 7. It depends on the weak acid and the weak base. If both of them have the same, the weak acid has a Ka that is equal to the Kb of the base, then the pH will be 7. It will be a neutral salt. Okay. Type. Another thing here that we have to remember very well, that if you are titrating, as we said here, a weak acid against a strong base, we said that there will be a jump like this, and then the buffer region, and then the pH, and then the rise in pH until we reach a basic solution. So here we said that in the buffer region, we say that at this is called the equivalence point. At half the equivalence point, because this comes a lot in exams, either they bring it in on a curve, or sometimes they will ask you about it as an equation or whatever. They will ask you to from the curve to get the Ka value of the acid. So we will see that if you come to the half the equivalence point and go upward, here you are going to rise using the ruler upward until you meet the curve, and then you go to the y-axis where we have the pH. We say that the pH equals the pKa at half the equivalence point. Of course, this will be clear when we study the buffer. So this will the pH equals the pKa at half the equivalence point. So if they asked you to find the Ka value for the weak acid, you just come to the half the equivalence point, which is here 12.5. You go up and then you go right to the pH line. So the value that is obtained here will be the pH, which is equal to the pKa of the acid. And if you get the pKa of the acid, the Ka is equal to 10 to the power minus the pKa. To get the Ka, we take 10 to the power minus L pKa. Do we need to explain how the buffers forms on the curve? No. They just will ask you calculate or find out the Ka value from the curve or from the plot. That's what they are going to ask you. Okay. Sometimes they will bring it in the form of equations, but this will be in the buffer. Okay, when we come, here you don't have to explain to them how did you get it. Just get it. Okay, thank you so much. This is what I wanted to tell you. طبعا, of course, when we have, of course, we are going to solve problems about this part, which I'm going to say here. Rina, hello, ya Rina. It's okay, حبيبتي. It's okay. So if we have as nowadays they ask, طبعا you have to choose the indicator whose pH range lies within or lies on the vertical line of the equivalence point. And if we have a curve like this one, we cannot choose neither methyl orange, because as you see that methyl orange changed its color within the range of 3.1 to 4.4, and this part lies below the vertical part of the equivalence point. Even if there is an indicator that has part of it on the vertical line and another part below, at this curve, do not choose it. It must lie completely on the vertical line to choose it. Like, for example, here, the phenolphthalein, it changed its color from 8.2 to 10. So this part altogether, all of it lies on the vertical line, so you can choose it. Of course, they will give you the data booklet and including all the indicators. Yes, ya Omar?
Miss, what if the indicator does not cover the vertical يعني like the range of the indicator is smaller than the vertical line?
Okay, if like in the methyl orange, they said they will give you methyl orange and they will tell you what happens if you are titrating using methyl orange for such a reaction. That's what you are asking about yet?
No, Miss, I'm asking يعني مثلا like phenolphthalein, look, it's in the vertical line, but it's not covering the whole vertical line. Is that also allowed?
It shouldn't cover the whole vertical line. It should only lie, the pH range should lie on the vertical line.
Okay, I see.
But
Thank
it
you,
will
Miss.
not, no, there is no indicator that covers all the vertical line, no. But it should lie on the vertical line. Yani the change in pH should lie on the vertical line at any place. Yani here, if you take, for example, phenol red can be used because it changed color from 6.8 to 8.4. From 6.8 to 8.4, it lies on the vertical line. So you can choose it as well. Okay?
Okay, thank you, Miss.
You're welcome, dear Sel. You had a question?
Yeah, Miss, I was just gonna ask if phenol red works, and you already
Yes,
answered.
it works. It works, طبعا, الحمد. It works because its pH range lies on the vertical line, so you can choose it. But if part of it is lying below, even here, you cannot choose it. The pH range must, all of it lie on the vertical line. Sometimes they will ask you, what if we use methyl orange in the titration? What happens if because it came more than once in exams, what happens if we use methyl orange in this titration? So as you see that the methyl orange, the pH range of the methyl orange does not lie on the vertical line. So what happens when methyl orange is used? You are going to see that it will change its color normally. The pH, the titration, when we are doing the titration, you will see that the color changes from, if you are starting from the acid, for example, it will change from red to orange and then to yellow. And if you started with a base like here, it will change its color from yellow to orange and then to red. It will change as usual. But what is the only difference? The only difference is that it will give you a different equivalence point. It will give you a different equivalence point than the 25 because it started the curve early. It started to change its color early before the equivalence point was reached. And this means that you will get an inaccurate equivalence point. You will get a wrong equivalence point because it showed you the changing color. The end point, we call this the end point. Where the indicator changed its color, we call it the end point. So here the end point is not equal to the equivalence point. When we say that the pH range should lie on the vertical line, it means that the indicator should change its color, which we call it the end point, at the same place where the equivalence point is reached, which is the volume at which the acid is neutralized by the base. But if the indicator changed its color before the equivalence point, so of course it will give you an inaccurate volume for the equivalence point. So you cannot work with it. Tamam? Because this question came about 2 times in exams. So what if we have a diprotic acid? We said that diprotic acid means that it has 2 protons instead of 1. And these 2 protons can be obtained in the I mean that these 2 protons can be released during the reaction. Like, for example, carbonic acid. Carbonic acid has 2 protons. It's a weak acid, carbonic acid. Then it can ionize in the first part with 1 mole, or it can react with 1 mole of, for example, sodium hydroxide to produce the HCOO. Here we have NaHCO3, sodium hydrogen carbonate plus water. And then in the second step, the sodium hydrogen carbonate with another molecule of sodium hydroxide, it will produce sodium carbonate and water. So we'll see that there are 2 steps. So on drawing the titration curve, we'll see that we started with the 3 because it's a weak acid. then there will be a little jump before the gradual change, and then the first equivalence point, and then it will start once more, and then a second equivalence point, and then to the end. So here we have two equivalence points, not only one. One of them corresponding to the first step, where the carbonic acid reacted with sodium hydroxide to give this, and the other one when it started to continue the reaction with sodium hydroxide. Because if you add these two equations together to get the full equation, you will see that H2CO3 reacts with 2 moles of sodium hydroxide to give sodium carbonate plus water. So the mole ratio is 1 to 2. So if you are going to use the second equivalence point in your calculations, this is equivalent to the volume of the sodium hydroxide that completely reacted with the carbonic acid. If you are going to use the volume at 35, this means that you are going to use, يعني خلاص, the reaction, all the reaction is finished. So the volume of sodium hydroxide completely neutralizes the carbonic acid. So this is the volume where all the carbonic acid is neutralized. But if you are going to use the first half equivalence point, then you will get half the equation only, which is the first one. It means that this volume, you must multiply it by 2 in order to find out the volume of sodium hydroxide that completely reacted with the carbonic acid. Understand me? And here, if any problem, they asked you to find the concentration of carbonic acid. So you have to get the number of moles of sodium hydroxide that reacted with it. So if you are going to use this volume, which is the 35, you are going to use it at once. So you say that the number of moles of sodium hydroxide is equal to the concentration times volume. And so the concentration, for example, is 0.1 times the volume, which is 35 over 1,000. So you get the number of moles of sodium hydroxide. You substitute directly here. You get the number of moles of carbonic acid, which is half this value, half the number of moles of sodium hydroxide, and from which you can get the concentration of the carbonic acid. But if you are going to use this volume, which is 17.5, you have to multiply it by 2 first, and then substitute in the number of moles of sodium hydroxide. You understand what I'm saying? How do you choose an indicator for diprotic acids? That's what I'm saying, Hadr Yasali. Hamza is asking, how do we choose an indicator for the diprotic acid? You can choose an indicator here, and you can choose an indicator that will change its color within this range. But if you choose the indicator that covers this range, then the volume here, you must multiply it by 2. يعني when you are titrating, while you are titrating, please concentrate with me بس الأول وبعدين I'm going to answer your questions. يعني here, لا, don't يعني raise your hands and ask me whatever you want, but يعني here, please concentrate بس first. If you are using an indicator covering this range, then you will get the end point 17.5. So this means that you have to multiply this volume by 2 so as to get the number of moles of sodium hydroxide that completely neutralizes the carbonic acid. Okay? But if you are using an indicator in this part, so this means that the equivalence point will be 35, and this means that you can use it at once. You are not going to multiply it by 2 to get the number of moles of sodium hydroxide. Understand me? Understand me, Hamza, or would you like me to repeat? Hadri Ryan. Hamza, you understand, or would you like me to repeat? Tamam. Okay, you all understand what I said here? If you are using an indicator that lies in this region, so you have to use the volume that is here. But if you use this volume, it's going to be multiplied by 2 to calculate the total number of moles of sodium hydroxide that completely neutralizes the carbonic acid. But if you used an indicator that is present here, then it will give you directly the equivalence point, which is used to completely react with the carbonic acid. So you are going to use the 35 without multiplying by 2. Okay? طيب, Radwan, Can you repeat what you just said? I repeated it. Would you like me to repeat once more? And if you are going to use an indicator that will change its color in this area, in this region, then of course you are going to see that the volume here is 17.5. Okay. Tamam. Okay. So you have to multiply it by 2 to get the volume of sodium hydroxide that completely neutralizes the whole carbonic acid. Type, Ryan, you raised your hand.
I don't understand. Can you please repeat one more time?
Type, and I repeated it, but you were concentrating on asking. Would you please concentrate? If you use an indicator that lies in this region, okay? So where is your equivalence point? Is it this or that? It is this.
That's the half equivalence.
And this means that only one step was formed.
Yes.
Yani not all the carbonic acid was neutralized, but half of it only.
Yes.
So the volume you get it here, you multiply it by 2 to get the volume of sodium hydroxide that completely neutralizes the carbonic acid.
Okay.
Okay. But if you used an indicator that is present in this part, it changed its color. For example, between like phenolphthalein, from between 8 and 10, between 10 and whatever. So the volume here at the equivalence point, you are going to use it at once to know the number of moles of sodium hydroxide that completely reacted with the carbonic acid. Yani it means that you are in this step where the 2 steps were formed. Okay. Sally, you had a question, I think. Well, you're welcome, Ryan. Huh? Sally?
Yes, I did. So you know how here at the bottom when you were working out the concentration of carbonic acid?
Yes, you can get the concentration of carbonic acid by knowing the volume at the equivalence point. So you will get the number of moles of sodium hydroxide, which is double the number of moles of carbonic acid. So this means that the number of moles of carbonic acid will be half the number of moles of sodium hydroxide. And by knowing the volume you started with in the titration that you placed in the conical flask, the volume and the number of moles, you can get the concentration.
So the volume, is it the whole thing that they say?
The volume of carbonic acid that you started in the conical flask. And for example, they said that they took 25 centimeter cube of carbonic acid.
Okay, so it's not like the total.
No, it's not the total. لا.
Okay, thank you, Miss.
You're welcome, dear. خلاص, you all understand this part? Because nowadays, يعني in the last 4 exams or 5 exams, they started to ask about the diprotic acids. Before they didn't ask about them, but nowadays they ask about them. Of course, يعني I'm preparing a question. يعني concerning how to draw the curve of such a, يعني how do we deal with such questions. طبعا, as you see here, that of course we can see it in the question that I'm preparing. Okay, now we come to the buffer solutions. I'm just revising كده quickly, and then I'm going to solve questions with you. Okay, now when we come to the buffer solutions, we said that a buffer solution either you say that it is a solution. When they ask you a definition, you say it is a solution that resists the change in pH, that resists the change in pH, or you can say that it is a solution whose pH does not change significantly, Either you say this or that. This is a mark. And then you have to say on the addition of a small amount, of an acid or a base, And we know that buffers could be acidic or could be alkaline. Yani, for example, if you have an acidic buffer, this means that it consists of a weak acid and its salt. And one of its salts, it could be sodium, it could be ammonium, could be potassium, whatever they write. It is a weak acid together with its, both are present in the same solution. The weak acid ionizes to give H positive plus ethanoate ion negative, and the sodium salt completely ionizes, or if it is potassium or ammonium, it completely ionizes to sodium ion and ethanoate ions. Now, how does this buffer work? Now, we say that if a small amount, there should be a small amount, otherwise it will change completely. If a small amount of an acid is added, so what will happen? We look at the equilibrium. Yani when we discuss how does the buffer work, we have to look at the equilibrium equation. It doesn't mean that the other equation is not present. La, of course it is present. But when we talk about how does it work, we look at the equilibrium. Now, at the beginning, we have to say, there are always 4 marks for such a question to ask you what happens. So at the beginning, you have to say that there is a large reservoir. There is a large reservoir of both ethanoic acid. If it is ethanoic acid, it could be butanoic, could be propanoic, whatever. And salt, which is our base, our conjugate base, which is the COO negative. At the beginning, there is a large reservoir. If you do not remember the word reservoir, it doesn't matter. Say there is a large amount at the beginning. There is a large amount of both ethanoic acid and ethanoate ion, but they usually use the word reservoir. But if you don't remember it, say a large amount, okay? So what happens when a small amount of acid is added? So as I told you that when a small amount of acid is added, we start back to look at the equilibrium position. So this is an acid. So it will react with what? In the buffer, you have these two, the ethanoate ion does not come from the acid itself, but it comes from the salt. And the amount that comes from the salt is much, much bigger than the amount that comes from the acid. So when an acid is added, it will not react with an acid like itself. It will react with the ethanoate ion, which is the base. So here we say that the ethanoate ion will react with the H positive, forming the CH3COO minus, which means that when you add here the H positive, it will react with the ethanoate ion and the equilibrium. That's why I told you that you have to look at the equilibrium step. So when a small amount of acid is added, it will react with the ethanoate ion, forming ethanoic acid. So the concentration of ethanoic acid increases slightly. We say increases slightly, whereas the concentration of the ethanoate ion decreases slightly because it reacted with the acid. Decreases slightly. And so the concentration, so the ratio between them, the ratio between the concentration of the acid to the concentration of either we say the salt or the conjugate base, changes slightly. So the pH, so does the pH. It means that if the concentration of the ethanoic acid increases slightly because the equilibrium shifts to the left-hand side, and the ethanoate ion decreases slightly because it reacted with the H positive, then the ratio between them will change slightly, and so does the pH, it will change slightly. What if we add hydroxide? What if we add hydroxide ion? If you add hydroxide ion, which is a base in small amount, so what will happen? Will it react with the base like itself? No, it will react with the acid. So it is the CH3COOH will react with the hydroxide ion, forming the ethanoate ion plus water. And this means that the equilibrium will shift towards the right-hand side. So this means that the concentration of ethanoic acid decreases slightly this time because it is the one that reacted with the hydroxide. It decreases slightly, whereas the concentration of the CH3COO minus, which is the salt, corresponds to the salt, increases slightly. So we repeat what we said, that the ratio between them slightly changes, or does not change significantly. Either you say slightly change or does not change significantly. So the ratio between them does not change significantly. So does the pH. It means that the pH also will not change significantly. And of course, we have a problem in the book, and it comes in exams. It comes that what happens if you add a certain amount of an acid. What happens if we add an acid, for example, to a buffer like this? Show what will be the change in pH. Let me get the question. It says that if we have a buffer like this one, and the pH of this buffer is 4.76. It is 4.76. This is the pH of the buffer. Of course, from a previous step, we calculated the pH of the buffer. I'm going to show you how. طبعا, I will start by showing how do we calculate the pH of the buffer. For example, if we are starting with what was the values بس عشان if we started with a concentration of ethanoic acid, طبعا هنا we have the Ka value as long as we have the equilibrium. And if you have a buffer, we said that here we have a Ka value because there is an H positive plus we get the CH3COO minus plus LH positive. And here we have the salt, which is the CH3COO Na. It completely ionizes to give the CH3COO minus plus the sodium ion. So how do we get the pH of such a buffer? If we started with, for example, if they said that they started with a concentration of ethanoic acid, for example, to be 0.5 mole per decimeter cube, the concentration of ethanoic acid, if it is 0.5 mole per decimeter cube, and the concentration of the salt, for example, it is, for example, 0.1, whatever. And here they took it the same, 0.5, but I don't want to take it 0.5. I want to show you that it differs if it is 0.6 mole per decimeter cube. So how do we calculate the pH of such a buffer? Then we say that here, since we have Ka, we say that the Ka, yes. Can we say OH reacts with hydrogen ion to form? When do you say so, yeah, Sif? لا, we don't include the water here.
No, miss, I was just asking from the previous where we add the OH minus.
انت بتتكلم على الويك اسيد. how can we calculate ال pH بتاعت ال strong base?
No,
ولا
the
بتتكلم على
talking
ايه؟
about how adding a based a buffer, like how does that affect it?
Is that if you added a base, yes, okay, you want to complete here if we added a base, طب ما هو احنا قلناها هنا اهي. If you added a base,
So
ولا
I
انت
mean, can you
قصدك
just
ايه؟
say the OH reacts with the H plus just to
yes,
form
you
water
can say
only?
so. Yes, you can say so. هنا Saif is asking me, can we write, instead of writing this equation, can we write that the H positive reacts with the OH minus reacts with the H positive, forming water, and so the equilibrium also will shift towards the right-hand side to produce H positive once more. Yes, you can write it. Yes.
Okay, thank you, miss.
Either you write this equation or you write that the H positive reacts with OH minus, forming water, and so the equilibrium also will shift to the right-hand side to regain the hydrogen ions once more. Yes, you can write so. So here we said that the Ka is equal to, as we usually say, it is equal to the concentration of the hydrogen ion times the concentration of the ethane weight ion divided by the concentration of the ethanoic acid. But when we talked about the weak acids, we said that we are going to consider the H positive and the ethane weight ion equal, and we say equal H positive square. But here we cannot do that. If you do that, it will be very wrong, because the ethanoate ion does not come from the acid only, but it comes also from the salt. So the concentration of the ethanoate ion is not equal to the concentration of the H positive. It's not 1-to-1 now, because a big part from the ethanoate ion comes from the salt. So you cannot assume that the ethanoate ion concentration is equal to the H positive concentration. So we will not do that. So we will leave the equation like this, but we will rearrange it to say that the H positive is equal to the Ka times the concentration of the acid divided by the concentration of the salt, of the base, the conjugate base. And so we, of course, they will give you the Ka for the weak acid. And now we can have the concentration of the ethanoic acid, which is 0.5, and we substitute by the concentration of the ethanoate, which comes from mainly from the sodium ethanoate by 0.6. So you are going to put this 0.5 and this 0.6, and you have the Ka, you get the hydrogen ion concentration, from which the pH equal minus log the hydrogen ion concentration. Okay, so what if they didn't give you the concentrations? What if they give you the volume and the number of moles? So here, if they give you, if in another problem, they didn't give you the concentration right away, they said that they started with, for example, ethanoic acid having a concentration equal to, for example, 0.1 mole per decimeter cube. And they started with a volume equal, for example, 25 centimeter cube. For example, I'm saying any numbers. And the sodium ethanoate, they started with a concentration equal 0.1, and the volume is equal to, for example, 30 centimeter cube. So what are we going to do here? Are we going to use the concentrations that they gave us? No, because they gave us volumes. So here they can say that the total volume is, for example, 1 decimeter cube. For example, they can say so. But here, as they gave you the concentration and the volume for each, first you have to calculate the number of moles of ethanoic acid, which is equal to the concentration times volume. So 0.1 times 25 over 1,000. So you get 2.5 times 10 to the power minus 3, for example. And the number of moles of the sodium ethanoate to be equal to 0.1 times 30 over 1,000, which is equal to 3 times 10 to the power minus 3. Now you calculated the number of moles from which you are going to get the new concentration. When you added these two together, each one of them will have a new concentration. So the concentration of ethanoic acid, the new one, it's not going to be 0.1, but it's going to be the equal to the number of moles divided by the total volume. And so here we are going to get the number of moles that we got here, 2.5 times 10 to the power minus 3, divided by the total volume, which is 55 over 1,000. And you get the new concentration. And for the sodium ethanoate, you will do the same, that the concentration of the new concentration of the sodium ethanoate is equal to number of moles, which is 3.0 times 10 to the power minus 3 over the total volume, which is 55 divided by 1,000. And you get the new concentration. Yani, since they give you volumes and concentrations, you cannot substitute by the concentration given directly in the rule. You have to calculate the number of moles first, and then divide each number of mole by the total volume to get the new concentration. And then the new concentrations, you substitute by them here in the equation of the H positive. What's the K value here? Yani, as if it is given, yani, Rayan, whatever they give you, because I don't remember yani, numbers. They will give it to you. Okay, yes, Ali?
But sometimes they ask for you to find the Ka. So in this case, would I just keep the equation the same?
If they are asking about the Ka, yes, the equation is the same, but they must give you the hydrogen ion concentration or how to get it. Yani, at the beginning, you have to get the hydrogen ion concentration by giving you yani, any information that will give you the hydrogen ion concentration. Yani, if this is unknown, then this must be known. They must give it to you. They must say that the pH of the buffer is so and so. Understand me?
Yeah, okay.
Yeah, you understand ولا shall I repeat? يعني if they are
لا لا
asking, yes, تفضل.
Miss, يعني, you know, for example, in the weak acid, the ethanoic acid, usually if it's 0.1, for example, so the hydrogen ion would be half of that. So do I just use that as the
لا
hydrogen ion?
مين اللي قال ان the concentration of hydrogen ion is half? No one said so. And if you have a weak acid, CH3COOH partially ionizes to H positive plus ethanoate ion, right? Is the concentration of the hydrogen ion half this value? No.
No,
Because
I'm just saying assume, يعني, from
لا,
the question.
you don't assume. يعني you assume يعني now ولا إيه? Because it can be half. Because if you have a weak acid, the dissociation is between 1 to 10%. We don't know it. It's between 1 to 10%. In some acids, they dissociate only 1%, and mostly they can dissociate to 10%. So we cannot assume them that it is half. Understand what I say? Yeah, understand what I mean يعني? But they must give you, يعني if you want to calculate the Ka value, we said that the Ka is equal to the H positive times the ethanoate ion negative. This is in a weak acid. We are not talking about the buffer now, isn't it? You are talking about a weak acid. So here, if they don't know the Ka, which is equal to H positive squared divided by the concentration of the weak acid, they must give you the pH equal, for example, any number, مثلا 1.5 times 10 to the power minus 5. They must give it to you. أو طبعا يعني they will not give you such, يعني they will say, for example, that the pH equals, for example, 5. For example, 5.2. So first, you have to get the hydrogen ion concentration, which is 10 to the power minus 5.2. And when you get the hydrogen ion concentration, you will substitute in this rule. And by knowing the concentration of ethanoic acid, for example, that you started with, you can get the Ka. Understand me, Yaseli?
Yes.
Understand ولا shall I repeat?
لا فهمت. Thank you.
تمام, okay. Yes, Adham, you have a question?
Yeah, miss. For the concentration of the ethanoate ion, do we always assume it's equal to the concentration of the sodium, the one with sodium?
The sodium ethanoate, يعني the salt?
Yeah.
Yes, because it comes mostly from the salt. يعني this part comes only from 1% to 10%. It's a very small value. And usually they say even 1%. So the concentration of the ethanoate ion mainly comes from the sodium ethanoate. واخد بالك يعني if this is, for example, 5 and this is 0.001, so it's 5. واخد بالك؟
Oh, so we ignore it, صح?
Yes, as you know, the number of moles and concentration of the sodium ethanoate, then you will know the number of moles of the ethanoate ion only, because it's equal, يعني we consider it equal to the sodium ethanoate.
Okay, thank you, miss.
You're welcome, dear. Any other questions here? Type. So here, yes, here I am.
Can I use the rule H plus equals Ka times concentration of acid over salt?
طب ما هو ده اللي انا مستخدماه هنا يا ريان اهو.
Okay, yeah. Because I don't know it as like, I just know it as the formula. I didn't know it was that.
لا, يعني I wrote the original formula first and then I rearranged to get the hydrogen ion concentration. Okay. طيب, if we have such a buffer and the added, for example, the buffer that we used was its pH was this value, and they added a small amount of acid. يعني, for example, what happens if they add 0.01 moles of acid? And if I have, yes, another question. Yes, Ryan. طيب, so here, what happens if we add بقى if we add, let me write it in a different, يعني what happens if 0.01 moles أو mole per decimeter cube أو moles of HCl is added to such an يعني طبعا here it must be smaller than this one. So for example, what happens if we add 0.001 mole of hydrochloric acid to this buffer? So what happens? Then we said that the acid will react with the base, or with the conjugate base. And here either we say CH3COO-Na, but it's better to say here it's CH3COO minus. And here we have also the CH3CO minus. Okay, so what happens if we add 0.001 mole of HCl? As we said that it will react with what? The HCl will react with the ethanoate ion. So this means that here we have 0.003 and here we have 0.0025. So what happens if I add 0.00 mole of HCl? It will react with the base, the conjugate base, to form the acid, as we said. So this means that the number of moles of the CH3COO minus will be equal to 0.003 minus 0.001. It becomes 0.002. And the number of moles of the ethanoic acid now will increase by the same value. We started with the acid to be 0.002. We add to it the 0.001. It becomes 0.003. Okay. And so we substitute by if you substitute by these values in the equation, you will see that the pH will not change significantly. Would you like me to make it يعني? I did it, but يعني, would you like me to complete? And here, if they said that 0.001 moles of HCl is added to this buffer, so show that the pH does not change significantly, as we said here. We said that the pH does not change significantly on the addition of a small amount of acid. So we want to prove this. So if they said, after we calculated the number of moles of ethanoic and the number of moles of ethanoate, so if 0.001 moles of HCl is added, it reacts with the base of the salt, of the conjugate base of the acid, to form more acid. So this amount will decrease by the value of the HCl that is added. And this amount of ethanoic acid will increase. So this is 0.0025. So it will be 0.0035. And then you take these two values and you substitute to get the concentrations. And of course, you will not add the volume of HCl added. Yani they are going to write to you that as if its volume is not present. So you calculate the new concentrations and you substitute here. You will see that the value of the pH, here it was 4.76, it will be 4.74, for example, or 4.73 or 4.75, and it will not change significantly. Understand this part? But if it is added to water, if you add the same amount of HCl, it's usually they say 0.01 moles of mole per decimeter cube of hydrochloric acid. If it is added to water, we know that HCl is a strong acid, so the pH is equal to minus log the 0.01, it will be 2. And we know that the pH of water is 7. So this means that the pH of water will decrease from 7 to 2. So this is a very big change. But in the buffer, it will change by only 0.0, for example, 2 or 0.03 or something like that. The change will be so little. Understand me, Jama'a, or do you have a question? Any questions? But what happens at half the equivalence point? As we said that if we we said that in the titration curves of a weak acid with a strong base, we have something like that. We said that this part is called the buffer. The buffer, in the buffer region, there is a slight change in pH because in the buffer region, as we add small amounts of hydroxide ions to the acid, the pH does not change significantly because now we are having the acid, the weak acid that we are having, and we are adding to it sodium hydroxide. So it formed the buffer because these two together they will form the salt, which is the CH3COONA. And so we have the weak acid together with the salt in this region, and this forms a buffer. And that's why here in the buffer region, you will see that there is a gradual change in pH. The pH is not changing significantly. And so we say that at half the equivalence point, the concentration of the acid is equal to the concentration of the base, the conjugate base. And this means that here, if I rearrange the above equation, we said that H positive equal Ka times the concentration of the acid divided by the concentration of the base. So since are both equal, they will cancel. It will be 1. And this means that the H positive is equal to Ka. At half the equivalence point, the H positive is equal to the Ka. If we take minus log both, then it will be pH equals the pKa. That's why we said that if this is the equivalence point, we take half of it. This is half the equivalence point. As I showed you, you go like this. This is pH. So the value that you get here, the pH is equal to the pKa. Understand me? At once, at half the equivalence point, the pH equals the pKa. Do you have any question here? Any questions? طب let us see بقى كده exam questions. Yes, Ryan.
Miss, so for example, sometimes in the exams they bring you the same concept, but instead of giving you a graph, they give you, for example, the volumes of the acid and the salt, or the base, sorry, and they're half of each other. Does that mean it's the half equivalence point rule?
Yes. If the ratio between the acid and the base is 1:1, and they give you the same concentrations and the volume of one of them, then and they give you half the volume of the other, this means that it means that it is half the equivalence point. Yes.
But they have to have the same concentration, yeah?
If they have the same concentration, yes.
Yeah, okay, thank you.
Okay, you're welcome. طب let us see بقى questions. Let me show you the questions in exams, important questions. Let me see, for example, May, I'm going to start with this. And of course, whenever we have time, we are going to complete, because this I wrote on it, very important. May 2024, if we have May 2024. Number 19. This is number 19. Of course, I'm not going to go through it all. I just want to show you. طبعا they said here, if you can see the page. Can you see the page? You can see it, I think.
Yes, Miss, we can see.
Yes, we can.
See it? Okay, thank you so much. So they said here, this is number 19. They said complete the equilibrium labeling the acid base as A1, B1, and A2, B2. So of course here we see that from the Ka values, they gave you the Ka values upward, I think. They should give you the Ka values. So if we have, what were these? 1 minute. This is propanoic acid and methanoic acid. So when we look at the values here, this is propanoic acid and methanoic acid. We see that the Ka value of the methanoic acid is stronger. It is greater than the Ka value, or the pKa is smaller. So this means that ethanoic acid is the stronger acid. When we compare this, the ethanoic acid, the methanoic acid is a stronger acid because the Ka value is greater. And so here, when we complete such an equation, the methanoic acid is acid 1 because it is the stronger acid. They said labeling acid 1, يعني it doesn't matter. And this will be base 2. And then the methanoic acid is going to give a proton to the propanoic. And so it will form the CH3, CH2, COO, H2 positive, plus HCOO minus. So this will be base 1, and this will be acid 2. Okay, we have to say acid 1, base 2 gives يعني here this is acid 1 and this is base 2, and then the يعني whatever بقى is the conjugate, we say base 1 and acid 2. خلاص طيب. Let us see بقى what did they say afterwards. They said here a student measured the pH of separate 0.05 mole per decimeter cube solutions of the chloroethanoic acid and dichloroethanoic acid using a pH meter. He used concentrations of 0.05. The concentrations is 0.05 mole per decimeter cube of both. And then he assumed that the H positive equal A minus. You see, this is an assumption we can use. And that the HA equilibrium equal HA initial. They said discuss the differences between the students measured and calculated pH values. This is the measured and calculated. In your answer, you should show how the student calculated their pH. They gave you the Ka value. So as we know that the hydrogen ion concentration for a weak acid is equal to the square root of Ka times the concentration of the acid. So we are going to calculate the pH for the chloromethanoic acid for the first one is equal to the square root of the Ka value, which is 1.4 times 10 to the power minus 3 times the concentration, which is 0.05. You get the hydrogen ion from which you get the pH value. And the same you are going to do for the second weak acid. You say that the H positive for the dichloro is equal to the square root of Ka, which is 4.5 times 10 to the power minus 2 times 0.05. And then you get the pH by taking minus log the value that you got upward here. Type. They said explain with reference to the assumptions made why there is a difference between the calculated and measured pH. طبعا, of course, يعني we see that the assumptions, we assume that the hydrogen, the concentration of the acid at equilibrium is equal to the concentration of the acid initially. And of course, this is not, this is an assumption. It's not something that is يعني real, because the acid dissociates, يعني part of the acid dissociated. It does not, the concentrations will not remain the same because the acid dissociated. So part of it is changed to the ions, the hydrogen ion and the negative ion. And this means that the initial concentration must be less than the concentration at equilibrium. The initial concentration must be greater than the concentration of the acid at equilibrium, because part of it dissociated into H positive and A minus. Okay. So as we said that here we see that when we calculate the pH, we will see that the calculated pH is less than the measured. Yani first you are going to calculate and show them that you got the values. And here we say that the calculated pH is lower than the measured pH, because in the calculated pH, we assume that the HA is equal to the equilibrium, although it is smaller than the HA at equilibrium. We used the initial instead of using the concentration of the acid at equilibrium. And because here the dichloro, as we have taken before, that the dichloroethanoic acid is a stronger acid than the monochloro, So that's why there is the difference here. If you see the difference here, it is 0.2, and the difference here is 0.03. So you will see that the difference here is greater than the difference here between the calculated and the measured, because the dichloroethanoic acid is a stronger acid than the monochloro. We have studied this, that the more you have of chlorine atoms which are electronegative, they will withdraw the electrons away from the hydrogen, facilitating its removal. So that's why the dichloro is more acidic than the monochloro. And we'll see that the difference between the calculated and the measured is greater because this is a stronger acid than this one. You understand this part, or do you have a question?
Miss, can you explain why the chloro is weaker?
Because if you have only one chlorine in the monochloro, and you have only one chlorine withdrawing the electrons away from the hydrogen,
Okay.
compared to two. Here, there is only one chlorine. Here, there are two. Okay.
Miss, can I say that for the one chloro, it's gonna cause less dissociation of the acid?
Yes, you must say that the chlorine is an electronegative atom. It withdraws the electrons away from the hydrogen, together with the oxygens طبعا as well. The more the chlorine atoms, the more the withdrawal, and this will make it easy for the hydrogen ion to go outside as a proton.
Okay, Miss, thank you.
تمام. طيب, this is the first part of the question. Now we come to the second part, which they want you to draw this curve. They said 4-hydroxybenzoic acid is a diprotic acid. We can see that it is a diprotic acid because you see that there is a proton here bonded to the COOH, and there is another proton here bonded to the oxygen. This is not an alcohol. This is called a phenol, C6H4. When it is bonded here, whenever you have a phenol, it differs from, this is called phenol. So in the phenol, the hydrogen ion is slightly acidic. It's not an alcohol. In the alcohol, the hydrogen does not get out. The alcohols are neutral. But phenols, the C6H4 is a phenol. So it is bonded to a carboxylic group. And so we know that the hydrogen in the carboxylic group is acidic. And here, because it's a phenol, also this is acidic. So that's why we have two protons. And they say that it is a diprotic acid, which dissociates in two stages. Each stage has a different pKa value, okay? So they said that the first dissociation, this hydrogen comes out in the form of a proton plus the rest of the molecule in the negative ion. The pKa value is 4.5. So the first pKa 1 is 4.5. And for the second, the pKa2 is equal to 9.3. So the second proton to be removed is removed at a pKa of 9.3. خلاص? Now they said in a titration, 75 centimeter cube of 0. They said that in a titration, 75 centimeter cube of this concentration of sodium hydroxide was added to 25 centimeter cube of this acid. Complete the titration curve. Now, first, when they added the sodium hydroxide to the acid, this means that the sodium hydroxide was the one that is present in the burette. So we don't know the equivalence point. So to get the equivalence point, we have to get the number of moles of the acid, which is equal to 25 over 1,000, times its concentration, which is 0.025. So what do we get here? Let me do it on the calculator. So here we have 25 divided by 1,000 times 0.025. So I got 6.25 times 10 to the power minus 3. 10 to the power minus 3. And since the more ratio for the first pKa, we said that this means that only one of the protons went out, right?
Miss,
So yes?
I got times 10 to the power minus 4.
Minus 4 or minus 3? I got it minus 3. Let me do it once more. 25 over 1,000 times 0.025. Yes, maybe I wrote something else. Yes, thank you so much, Yasir. So this is 6.25 times 10 to the power minus 4. And since the mole ratio is 1:1 for the first step, the first only proton that went out, then this means that this is also the number of moles of the sodium hydroxide, from which we can get the volume of sodium hydroxide for the first step of the equivalence point to be equal to the volume equal number of moles over concentration. So 6.25 times 10 to the power minus 4 over the concentration, which is 0.025. So what will be, this is divided by 0.025. I got 0.025 decimeter cube, which means 25 centimeter cube. So this means that the first equivalence point is at 25 centimeter cube. Okay, now we said that if we have a weak acid that is titrated against a strong base, they also said that the pKa1 is 4.5. It means that at 4.5 pH, because here we will have this buffer region. You see that they started with the curve, they rose the pH, and then we have the buffer region. The buffer region at half the equivalence point, which is the 12.5, you will see that the pKa is, as they said, which is the 4.5. Okay, so we are, this is the pKa value, which is equal to the pH at half the equivalence point. So either you got the half the equivalence point, and then you know that the equivalence point will be double that, or else you do the calculations. Now, this is a weak acid titrate. You understand this part before I proceed? Either you get the equivalence point from the calculations, or else because they gave you the pKa value to be 4.5, you come to the 4.5, you go to, because it's equal to the pKa, you get here and go down, then this will be half the equivalence point. You multiply it by 2 to get the equivalence point, which is 25. Either you do this or that. Okay, and now, since it is a weak acid titrated with a strong base, then we said that the pH at the equivalence point will be about 6.5, about here. So you have to draw, this is the, if this is the half the equivalence, if this is the pH at the equivalence point, then this means that we have to تقريبا to get double here to start the new step. Okay.
So I have a question.
Yes.
Miss, so for the line we just drew, when do I know when to stop it? Because here we stopped at 8, for example.
Because I said that the pH is, the pH is at half the vertical line.
Okay.
So if the vertical line here is, as I've drawn, for example, it started, كده approximately, it's not something that is definite, but as we have seen in the pH titration curves, that if you have a weak acid titrated with a strong base, then the pH at the equivalence point is about 6.5, as we have said,
yes.
Right? So you started the end point like this, so this part should be nearly equal to this part to start the second step. Okay?
Yes.
Type. So we said that the equivalence point is at 25, and this shows only one step. So this means that to show both steps, then the volume will be double. Instead of having 25, it will be 50. The second equivalence point should be at 50. Okay? It should be at 50. Why? Because the first step is 25. So to complete the equation, to complete the reaction, it will be double. Okay? You understand? And also here, if you have 25 and 50, it means that between them, the midway between the 25 and 50 will be 37.5. It's here. So if you go up at 37.5, 37.5, and it will meet with, this is the 37.5, it meets at 9.3 here. This is half the equivalence point. Okay, we said that the pKa is half the equivalence point. So this is half the equivalence point. And so we have to also draw a gradual change through the half the equivalence point until we reach the second equivalence point like this. And then you have to draw it like this. Okay, the second step should be, the volume should be double the first, because in every step only one proton is removed. So if you add these two equations, you will see that you are not going to add these two equations, but I mean that only one hydrogen proton is produced here and only one proton is produced here, and they will not bring you anything else. So this means that the volume of the first equivalence point will be half the volume of the second. So if either by calculation or by using the curve they showed you that the half the equivalence point is at 12.5, if they showed you that it is at 12.5, so this means that the equivalence point is at 25. The equivalence point is at 25. Okay, so you draw the first equivalent point. The second will be double the first. So 25, it will be 50. And the peak and the second pKa, it's at 9.3. So this is half the equivalence point. And this will make you sure that also the endpoint, the second endpoint is at 50. So you draw it in this way. Understand? Well, would you like me to repeat anything? You understand how to draw this curve, or would you like me to
Can you
repeat?
please explain the second stage one more time?
Isn't the first equivalence point at 50, at 25? So what will be the second? It will be 50.
So the second
So
equivalence point is always at double the first
double the
equivalence point?
first, yes, because in the first step one proton is removed, and in the second also one proton is removed, so it will take the same volume. From 25 to 50, it means 25 as well.
Miss,
Okay.
would we lose marks if we didn't like the lines after the equivalence point, if they're not like really the same?
What do you mean?
Like, Miss, how do we know like where we end the curve for the first equivalence point and the last?
The last, they ended it to us. It was drawn in the curve. And how did we end this? We said that here, if you are titrating a weak acid with a strong base, the pH is about 6.5. Right? We said that this is the equivalence point. So to complete this, it will be a curve like this here. There is no place between this and this unless you complete this part, right? Okay, Safe? So
it's also like we memorize the shapes of the curves of like strong acids and weak bases. And
no, I didn't say that you have to. Yes, you have to know when to make a rise like this and then a gradual change in a weak acid or a weak base. You are going to draw a curve, a little bit curve like this, and then before the gradual change. But the main thing that I told you you must know is the pH at, if you have a strong acid with a strong base, the pH is exactly at 7. If you have a weak acid against a strong base, then the pH is about between 5.5 to 6.5, in this range. If you have a strong base against a weak acid, then the pH will be about 8.5. You have to know this.
Oh, okay. Thank you, Miss.
You're welcome. Look at it in the book and take the values and know them. Okay, so here they didn't give us any space to draw, except because we calculated out, we know now from the pKa value, from the first pKa value at 4.5, they drew to us this curve. We can either get from the curve half the equivalence point, and by which we multiplied by 2 to get the equivalence point, or you do it by calculations as I did. خلاص? So we know that the first equivalence point is at 25. And so if you draw the curve, there is no, if you draw a line here, there is no part except this part to make it a curve. And so at at the 6.5, the value here, the distance here must be nearly equal to the distance above it before you start the second curve. Yes, Adham?
Miss, how did you know the first equivalent point is 6.5?
Yeah, half the equivalence point is 6. I didn't say it's 6.5. It's 10.5.
The first equivalence point.
The first equivalence point was 25. How do we know it?
Yeah, like how do you know it's at 6.5 pH?
I didn't say that it's pH 6.5. You mean the 6.5 is half the equivalence point. Sorry, is the pH at the equivalence point. How do we know it? As I'm saying to Safta right now, you can look at the curves. At the beginning of the lesson, I showed you all the curves, and we have seen that if you are working with a weak acid titrated against a strong base, then the pH at half the equivalent. Sorry, the pH at the equivalence point is between 5.5 to 6.5. You have to draw it in this way.
Okay, thank you.
You're welcome. Yes, there's another question. Safe. Can it lose more than one proton? It here lost 2 protons, one in the first step and one in the second step. I don't understand your question.
Sorry, one more question. Since it's a strong base and weak acid, isn't the like pH at the equivalence point supposed to be between 9 and 8?
If it's only one step.
Oh, okay.
If it is only one step, but here you have 2 steps. Okay.
Oh, okay. Thank you, Miss.
You're welcome. Any other questions? Understand how did we draw this curve? Okay. Any questions, Jama'a, in the drawing? This is what I wanted to show you. Let us complete the question. They said a student was given 50 centimeter cube of a solution of sodium hydroxide. The pH of this solution was 12.43. The student was asked to adjust the pH to 12. So he's going to dilute it by dilution with deionized water. The student did not have access to a pH meter to adjust his pH. Calculate the volume of the deionized water in centimeter cube the student should add to the original solution. So we have a rule that says if you are making dilution, C1 V1 before dilution is equal to C2 V2 after dilution. This is when you are making dilution only, you use this rule. So here they started with 50 centimeter cube. You can use centimeter cube. You don't have to change it to decimeter. And from the pH, we can find the hydrogen ion concentration. So here, the hydrogen ion, they said that, okay, so here they give you the pH. So the hydrogen ion concentration is equal to the hydrogen ion concentration is equal to 10 to the power minus 12.43. So can someone please do this calculation for me?
Message 3.7153.
3.1753.
No, 7153.
7153 times 10 to the power?
Negative 13.
Okay, so this is the concentration, thank you so much, of the hydrogen ion. So this means that the concentration of the hydroxide ion will be equal to 10 to the power minus 14 over, which is the Kw, over 3.17153 times 10 to the power minus 13. So we get the concentration of the hydroxide ion.
0.0269.
0.0269. Thank you so much. Now they want to change it into 12. So also the hydrogen ion concentration is equal to 10 to the power minus 12, which means 1 times 10 to the power minus 12, I think. And so the hydroxide ion concentration is equal to 10 to the power minus 14 over 10 to the power minus 11. And this will make, I think, 0.03 ولا how much?
0.01.
0.01, تمام.
And also it's negative 12, not negative 11.
Negative 12, yes. So it's 0.01. So the first concentration is 0.0269 times 50 equal the second concentration, which is 0.01 times the volume that we need to find out. So V2 here is equal to 0.0269 times 50 over 0.01. So we get a volume equal to, can someone do it? Well, would you like me to do it?
134.5.
134.5, thank you so much, centimeter cube. So this is the total volume of the diluted solution. So they said how much water should be added. So here we have to subtract 134.5 minus the volume that was present at the beginning, 50, and we get the volume that should be added. Okay, so here the volume that should be added in centimeter cube to dilute the hydroxide from pH 12.43 to pH 12. Okay, you got this? Well, do you have a question? Type. So this was one of the questions that I wanted to revise with you. Let us have another one. I would like to take the titrations. Jan 2024. Jan. So Jan 2024, number 19 as well. Number 19. No, 18. So this is number 19. طبعا في الأول it started as equilibrium. They said here propanoic acid is a weak acid. We calculated pHs. Calculate the pH of 0.5 mole propanoic acid. Now we come to here. They said sketch. They sketch the titration curve showing the change in pH when 50 centimeter cube of 0.5 mole per decimeter cube sodium hydroxide is added to 25 centimeter cube of propanoic acid of the same concentration, using your answers to be III and CI. So here first, طبعا, in the BIII, let us see, they wanted to calculate BIII, they said calculate the pH of propanoic acid that we are going to start with. So we said that the hydrogen ion concentration of propanoic acid, which is a weak acid, is equal to the square root of Ka times the concentration of the propanoic acid. So it's going to be the square root of 1.3 times 10 to the power minus 5 times the concentration of the acid, which is 0.5. And so the hydrogen ion concentration, let me do it. And if someone did it, it would be better. So
2.549.
2.459 ولا 549. تمام. Thank you so much. And so the pH would be minus log this value.
This times 10 negative 3.
It will be معلش. Times 10 to the power negative 3. So the pH will be
2.593.
2.593. Thank you so much. So here, this is the III, and they said CI. CI, they said calculate the pH at the equivalence point, at the point in the titration where half the acid has been neutralized. So we see that the pH, when they said here the number of moles of propanoic acid in a solution may be determined by titration with sodium hydroxide. We calculated the pH at the beginning. Propanoic acid is a weak acid. Calculate the pH of 0.5 mole. Then they said that the number of moles. They said that the number of moles of propanoic acid in solution may be determined by titration with aqueous sodium hydroxide. Calculate the pH at the point in the titration where half the acid has been neutralized. So we say they gave us the Ka value, I think. Where is this? They give us the Ka of propanoic acid. So at half the equivalence point, we said that the pH is equal to the pKa. So this means that the pH is equal to minus log 1.3 times 10 to the power minus 5. So we get the pH
4.886.
4.886. Thank you so much. Now they said بقى in the last part, they said sketch the titration curve showing the change in pH when we added this. From the number of moles, طبعا we start the titration curve at the pH of the weak acid, which is 2.6. And here we have 2, this is 3, this is 2.5. So this is about 2.6. Yani we will start from here. We'll start our curve from here. And since it is a weak acid, this means that there will be a rise in pH before a gradual change. Okay. Now we want to know we want to know the equivalence point. So we know the concentration of the acid. So they said 25 centimeter cube of propanoic acid of the same concentration. So the number of moles of the acid is equal to 25 over 1,000 times the concentration, which is 0.5, which means that we have, I think, 7.5 times 10 to the power minus 3. This is the number of moles of the acid. And so it's the same as the number of moles of sodium hydroxide. Number of moles of sodium hydroxide. So this means that the volume of sodium hydroxide required to neutralize the acid will be the number of moles over the concentration. So it will be number of moles 7.5 times 10 to the power minus 3 over the concentration. So it will be 25 as well, right? Over the concentration, which is 0.5. So the volume will be 25 centimeter cube. So this means that the equivalence point is at 25 centimeter. Sorry, this is not 25. 25, it means that it should be here. And it should be at 25. This is the pH. Okay. This is the 25. Now, they said that at half the equivalence point, the pH is 4.88. Yani it's here. It's about here. So if we go like this at half the equivalence point, which is the 12.5, this is half the equivalence point at 12.5, then our point is here. So this means that we have to draw a curve here like this and go gradual. There will be a gradual change like this. There will be a gradual change before we raise the pH. Okay. We said that if we are titrating a weak acid with a strong base, we said that the pH at the equivalence point is at 8.5. The pH, as I told you, you have to know this. And here, this is only one step. So the pH, if you are titrating, the pH at the equivalence point, if you are titrating a weak acid with a strong base, then the pH of the solution should be nearly at 8.5. So this means that if you raise the vertical line here, then approximately the distance here should be equal to the distance here. So starting from 11, we are going to do the curve. Now, what will be the pH at the end of the solution? This is what I wanted to tell you. So here, how do we get the pH at the end when they added 50 centimeter cube? So we know that the volume at the equivalence point is 25. So we calculate, you understand all these parts? Well, because I want to remove it. Okay, so we get the number of moles of the total sodium hydroxide added. Total sodium hydroxide added, which is equal to concentration times volume, which is 0.5 times the volume, which is 50 over 1,000. So we get 2.5 times 10 to the power minus 2, I think. And now we got the volume at the equivalence point, the number of moles of sodium hydroxide at the equivalence point. It's going to be طبعا we can subtract بس 50 minus 25. So let's do it like this. يعني. We are going to take number of moles, which is also 0.5 times 25 over 1,000. We get 5. Is it 5 times 10 to the power minus 3? ولا إيه? I think it's 5 times 10 to the power minus 3.
0.0125.
0.0 كم?
125.
125?
Yeah.
Okay. So, and here in the above one, we have 0.0025, right? So, ولا 0 واحدة بس. 0.0125. Okay. So, to find the number of mole, to find the pH at 50 centimeter cube, we are going to subtract 0.025 minus 0.0125. It will be 0.0125. So this is the number of moles after the equivalence point. So the concentration after the equivalence point, the concentration of the hydroxide ions after the equivalence point will be equal to the number of moles divided by the volume. So here, the total volume here, we are going to divide it by the total volume to get the new concentration of the hydroxide after the equivalence point will be 0.0125 divided by the total volume, which is 75 over 1,000. So can you please do this calculation?
1 over 6.
لا يعني give it to me in points كده. Yeah.
0.1667.
0.1667. So this is the concentration. So if we want to get the hydrogen ion concentration, it's 1 times 10 to the power minus 14 over 0.1667.
Uh, 6 times 10, negative 15.
Negative 15?
Yeah.
So what will be the pH minus log this value?
Miss
Wait,
14.
no.
13.
Excuse me?
I got power 14, not
Yeah, 14.
Because I was astonished because it shouldn't be higher than 14. So what will be the pH here?
13.2.
13.2.
13.2. So this means that we have to end our titration curve at 13.2. You see?
Miss, here we did the excess because there was more of the hydroxide than the acid,
Yes.
right?
Yes. Because the hydroxide ion is the one that you are titrating with, isn't it?
Yeah.
So you see that, let me revise once more. At the beginning, we got the pH of the ethanoic acid from a previous step. It was 2.8803. Okay, so we have to draw a rise in pH. And when we calculated the equivalence point, we found it to be 25, or else from what they gave us, that the pKa is at certain value. So it means that we have to multiply it by 2 to get the equivalence point. And then we know that if we are titrating a weak acid against a strong base, the pH should be about 8.5 in the middle. So we have drawn a rise in pH and then a gradual change till we reach the 25. And we rise a vertical line. If this is the half point, then approximately we take the same distance here before we do the curve. And then we calculated the pH. This is what we should know, how to calculate the pH at the end of the titration. Yani either we calculate the number of moles or else we subtract 50 minus the total volume of the added sodium hydroxide, it's 50. And the equivalence point is 25. So this means that there are left 25 centimeter cube of the sodium hydroxide after the equivalence point. So we multiply the 25 over 1,000 by 0.5, we got this value. And you don't have to calculate the number of moles in both. You subtract the volume, the total volume minus the volume at the equivalence point. You get the volume excess of the sodium hydroxide multiplied by the concentration to get the number of moles. The number of moles must be divided by the total volume to get the concentration of the hydroxide. You got the concentration of hydroxide to get the pH, the hydrogen ion concentration equal the Kw over the concentration of the hydroxide. You get the concentration of the acid from which you get the pH. So this is the pH. So you draw a curve like this. Okay, you understand this, or do you have a question?
Miss,
Yes.
if we use a pKa, we would go to 4 point, get the answer from the previous question and go to 4.88 and multiply by 2.
But you have to know, يعني to know the equivalence point, you mean?
Yeah.
So if you draw what do we call it? A rise in pH and then a gradual change. Then you will see if at 4.88 you can go to the curve that you are drawing to get half the equivalence point. But it will not be accurate as you, because they said حتى هنا they said from CI. In CI we got we got the equivalence point, I think. Did we get the equivalence point ولا لا at CI?
CI, we got the
half the the pH at half the equivalence point.
Yeah.
طيب خلاص, you are going to multiply it by 2 to get the equivalence point.
Miss,
But
because
I prefer
I
that
did
you
it,
do
but I
it.
got 23 as the equivalence point, not 25.
Well, that's why I say calculate the equivalence point from the relations that we have, from the volumes and concentrations that we have. It's better. Like what I did here.
So you'd first calculate the moles of the acid, and then we'd use the moles of the acid and the...
In the 1-to-1 mole ratio, this is the same as the number of moles of sodium hydroxide. Okay, by knowing the number of moles and its concentration, you can get the volume at the equivalence point.
Oh, okay.
تمام. You all got this يا جماعة ولا إيه؟ خلاص, you all got this? How to draw the titration curves? طيب.
Miss, just one more thing. We use the same moles because at the equivalence point, it neutralizes the... So it's the
Yes,
concentration is
because
equal.
the mole ratio between the sodium hydroxide and the propanoic acid is 1-to-1.
Oh, okay. Thank you, Miss.
تمام, you're welcome. طيب, we can continue this at what time other? If you have more time at Tuesday, for example, in the morning, beside the Tuesday in the afternoon, your usual time, I can take you Tuesday in the morning if you'd like to.
Yes, Miss.
طيب, okay, so we can continue the rest of the questions that I collected it for you, and to see how do we measure the buffer pH and so on. And if you'd like to, we can meet on Tuesday beside our time. We can meet on Tuesday morning. If it's 9:30, okay for you, we can. And please, as I told you, if you have any questions, you can collect them for me Tuesday 9:30 a.m. We can work together beside our time on Tuesday as well. Okay. And if you have any questions, please ask. Thank you so much. See you inshallah on Tuesday. Said, you have a question?
No.
Yes.
Okay.
Thank you so much, Miss.
You're welcome, dear. Ma salam.
Thank
Have a
you.
good day.
You're all welcome. Thank you, Hamza. Okay. Bye-bye all.